Hey, future medics. Today we're breaking down a huge concept in physiology, the difference between aerobic and anaerobic metabolism. And it's all based on oxygen, but why it's important is a big deal. And understanding this and what's happening at that cellular level will help you understand respiratory failure, lactic acidosis, shock, cardiac arrest, like what is happening at the very internal part of the patient. And then anything else that has to do with that, it's a little easier for you to understand. When oxygen is present, the cells are in aerobic metabolism. So they are using oxygen. And that is how we function at our normal baseline where everything is running efficiently and correctly. So remember our order is glycolysis, Krebs cycle, electron transport chain. Now glycolysis in nature is anaerobic. It doesn't use any oxygen. But the other two, which set up and give us our large ATP payout, rely heavily on oxygen. So when everything is running efficiently, we get quite a bit of energy, 36 ATP total, and very little waste. A little bit of carbon dioxide, a little bit of water, a little bit of heat, nothing that's that big of a deal. When things are not running correctly, we have to step down into anaerobic metabolism without oxygen. And this goes back to step one, glycolysis. Glycolysis can still produce energy, but just a tiny little bit of it. But it can do it because it's not in the mitochondria, it's in the cytoplasm of the cell. And it will produce 2 ATP, which will sustain you for a little bit, but it produces quite a bit of waste, which will poison the system. So think of glycolysis like a backup generator. It'll power the house for a little bit, and maybe not even the whole house, just pieces of the house. But if you rely on it for too long, it's absolutely going to fail. So what exactly are we giving up other than the payout of ATP when we don't have oxygen? Well, without it, our body can't send anything through the electron transport chain, so we can't get that big payout. But we also can't shift hydrogen ions. You know, for the pumps that we need to make our body work, we can't shift them. We also can't make ATP synthase, which is important for a number of things in our body. So this is a very large problem for organs that rely heavily on ATP, like your brain. Your brain actually uses about 20% of all the ATP made in your body. It's a huge consumer of energy. So is your heart, so are your kidneys. So the things that really heavily rely on ATP are going to be affected. Without oxygen, pyruvate is converted into lactic acid. And that is sent to make NAD, to keep glycolysis occurring. Because it's our backup generator, it's the only thing we have, we need some kind of energy. So instead of pyruvate entering the mitochondria, it's then turned into lactic acid. We make NAD plus with it. We keep glycolysis going. It keeps pumping out lactic acid. As a result of that, we drop the pH in the body, which sends us into metabolic acidosis. And when you get outside of a very small pH range that your body can run on, nothing works. This is why it's incredibly dangerous. This is also why a lactic acid finding in the blood is not a coincidence and it's not an accident. It's actually a report card on how the cells are doing. And it shows they don't have any oxygen going where it needs to go. Short term, anaerobic metabolism will totally keep you alive. Not for long, but it will. It's a backup generator. It goes as long as the gasoline and it works, right? So we need to reverse it because long term, it's just not sustainable. Lactic acid is building up. You're becoming acidotic throughout your entire body. Cells are swelling and dying, organs will start to fail. And this is how shock becomes multiple organ failure. We have to reverse an anaerobic process. So, how are we going to reverse this acidosis? You got to fix perfusion. When we fix perfusion, the body has a pathway now to get oxygen to the cells. They probably need a little excess oxygen, a little help to get things kick-started, but we have to fix perfusion or nothing can get anywhere. And when oxygen starts returning to those cells, the ones that are still available and haven't died, they will switch back to aerobic respiration. Lactic acid will shift back to pyruvate and be able to be turned into large payloads of ATP. Over time, pH will be able to shift back to normal through feedback loops, which we've talked about before, to maintain homeostasis. But when they get bad enough, they need some external help to make this happen. This is why we teach you in class airway, breathing, circulation. We have to maintain those at all costs because when you see a very sick patient, you're not just seeing bad vitals. You are seeing anaerobic respiration at the cellular level. So I need you to fix perfusion. I need you to fix oxygenation. I need you to make sure they are being ventilated properly if they can't do it for themselves. Because otherwise, we cannot reverse the acidosis that they are in, and they're not going to get any better. So, in closing, aerobic respiration, fantastic, with oxygen. Anaerobic respiration, no oxygen, not great, not sustainable. And hopefully this will help whenever you see and you're looking at your next critical patient, you really understand what's going on and why those ABCs are so important. I know you will. You're doing great. I believe in you, even if you don't believe in yourself right now. I'll see you soon.